All right. Hello to everyone. Um, we have another amazing speaker for our algorithms and complexity seminar series. Today, the speaker is Emily Fox, who is an associate professor at the University of Texas at Dallas. And today, she's going to talk about something that we are also super interested in, and that is just oblivious routing schemes and how to simply construct them. And I think this is a very nice algorithm that a lot of people hopefully also understand and can take something with them from seeing this presentation. And we're very happy to have you, Emily. So yeah. So, let me say one thing before before we start the presentation. So during the presentation, you should feel free to ask questions, and the way to do that is in the chat on the right. So if you have any questions, please use the chat. There's also a question and answering tab in AirMeet, but please use the chat because that's easier to monitor for me. And then I'll interrupt at a good time and will ask you a question to Emily. And of course, at the end of the talk, there will be plenty of time to answer some additional questions, and there will also be a session thereafter where we can just socialize and where you can ask maybe questions that are a little bit off topic or that you're just generally keen on, but that are not so much of general interest. Okay, with that said, I think we are ready to hear the talk. So please take it away, Emily.
All right, thank you. So yeah, I want to talk about some work I did last summer. Normally I am a computational geometry and topology person, but some of that work got awfully close to pure graph theory, and this is what resulted from that. So this is work concerning the transshipment problem, which is sometimes called the minimum cost flow problem without edge capacities. So we are given an undirected graph G, vertex set V, edges E. I'll use N for number of vertices and M for number of edges, like normal. And along with our graph, the edges have positive edge costs. I'm going to express the edge costs as a vector of positive real numbers, with the indices being the edges themselves. I'm going to kind of stick to this vector matrix language as I go for reasons that will probably be a bit more clear in about 10 minutes. So we have our graph, we have our positive edge costs, and we're also given a set of demands for the vertices. These can be positive or negative, and we have a guarantee that when you sum up all the demands, they should sum up to be 0. Okay, to define what a solution to this problem looks like, we need to take the edges and orient all of them in some arbitrary way. I'll let E arrow be this arbitrary orientation of the edges, and we'll let I sub G be the vertex edge incidence matrix for the graph G. So columns are vertices, and it'll help you take vertices and tell you which edges leave the vertices and which edges enter. The details of plus and minus 1, all that doesn't matter so much. I just want to use that so I can define a flow. So the way I'm defining a flow, it is a real valued vector to the oriented edges. And the intuition I want you to have is if I assign a positive number to an oriented edge, you can imagine sending flow in the same direction as the edge. A negative number would be sending flow backwards. And we say a flow routes this demand vector B if the vertex edge incidence matrix times F is actually equal to B. And the simple language version of this would be that if that equation holds, the amount of flow leaving each vertex is equal to the demand of the vertex. So when you have a flow, the flow itself has a cost. And to get the cost, you can sum over all the oriented edges, and you take the absolute value of the flow assignment for the oriented edge, and you multiply by the cost of the edge. So an edge that has a flow of +3 or -3, you'll still have 3 times the cost of that edge, contributing to your total cost. All right. And then finally, the goal for the transshipment problem is to find a flow that successfully routes the demand vectors B while also having the minimum possible cost. Transshipment generalizes shortest paths and undirected graphs. It also generalizes some problems from computational geometry and machine learning, like discrete optimal transport, or another way of saying it is computing what's called the Earth mover's distance. I'll actually talk a little bit more about those problems later in the talk. But first I want to say a bit more about just transshipment in general. So it is polynomial time solvable, since it's a special case of the minimum cost flow problem. And still the best algorithm is this one by Orlin from '93 that is strongly polynomial time, but quadratic. Recently, there have been some faster exact algorithms for the transshipment problem, and more generally minimum cost flow. These really kicked off with this 2008 algorithm by Deitch and Spellman. And one feature that all these algorithms have in common is that they assume that the costs and demands aren't too extreme, that they're all bounded by some integer value u, and that they are themselves integers. And for most of the ways I'm going to describe these running times, you should assume that u is some polynomial in the number of vertices. So if you take this recent line of work, there's been a lot of results. I'm not going to attempt to survey all of them, but the most recent one is this paper at Fox 2023. It's a deterministic, almost linear time algorithm. So when I say almost linear time, I mean problem size to the 1 plus little o1, and then we have a polylog in u. That solves the transshipment problem exactly. Okay, so we have a very fast exact algorithm for transshipment, and so you may be wondering why I'm bothering to talk about approximation schemes. And the reason is because, as we'll see, we can get the running time down a little bit more, but also I think the finding of approximation schemes kind of suggested that this is where things were going. So for a little bit longer than we've had really fast exact algorithms, we've had fast, almost linear time approximation schemes for transshipment. And that means for any epsilon greater than 0, you can compute a flow that successfully routes the demand vectors B with a cost of at most 1 plus epsilon times the optimal flow value, and do so in almost linear time for any constant epsilon. Sherman in 2017 was the first to describe one of these almost linear time approximation schemes, but there's been a large number of improvements since then, including work by myself and my graduate student Joshua Liu appearing at Fox 2023. And I should say I'm going to be focusing on sequential algorithms, classic models of computation for this talk, but a lot of this prior work after Sherman wasn't motivated so much by the sequential model, but they're actually trying to work in parallel and distributed settings. Usually the main goal is to compute approximate shortest paths, but it turns out once you try to do that in a distributed setting, you may as well be solving the transshipment problem outright. Okay, I'm going to briefly touch on the approach Sherman took for solving the transshipment problem, because that inspires what is still being done for the more recent algorithms. So Sherman actually described an approach to solve a more general problem where you're given some kind of linear system, ax equals d, and you want to find a solution x that makes the equation true, where you're also minimizing some kind of norm on the vector x. So what Sherman proposed is that you can take some kind of weak approximate solver that doesn't necessarily minimize the norm, doesn't even necessarily solve the equation exactly, but very nearly does so, and then repeatedly apply it to the residual right-hand side vector. So you get some solution x, you compute d minus ax, which tells you how close you were, and then you try to find some x2 that can solve a times x2 equals this residual over and over and over again. And the number of iterations you need before you finally get an approximation scheme, it depends heavily on this matrix A, and specifically on what's called the generalized condition number. And so Sherman proposes what we can do is find some other matrix P called a generalized preconditioner, where P times A is well conditioned. If you were to run this algorithm with P times A, you wouldn't have too many iterations. And let's solve this equation PA times X equals PD instead. Yeah. So that was Sherman's approach, and it was an approach directly used by a couple of the follow-up papers, including my own. But it turns out, even if you're not actually following Sherman's approach exactly, all of these almost linear time approximation schemes do kind of the same idea, where you use some kind of loose, relatively easy to get approximation for the transshipment problem, and you repeatedly run it and refine it until finally you're down to an actual approximation scheme. In fact, these algorithms all look so similar that in 2023, Goran proposed this boosting framework that pretty much exactly describes what all of these algorithms are doing and why they result in approximation schemes after so many iterations of this refinement. We'll actually be talking in quite a bit more detail about Zuzik's framework, because that's what I'm going to use in my new approximation scheme. Okay, so before I talk about the new result, I want to say some things that would be nice to see that aren't necessarily present in these past works. So first, I've also been saying almost linear time for the running times of these approximation schemes. It'd be nice if we had one that was near linear time, which I take to mean n or m times a polylog in the number of vertices times the largest capacity or demand. So some of these past works were actually near linear time. It'd be nice to have no runtime dependence on the largest cost or demand. In particular, it'd be nice to have either let you have very large costs or even irrational costs, ones that aren't integers or even real rational numbers. And as far as I know, this paper from myself and my grad student is the only one to directly work with arbitrary real costs and demands. Okay, and then finally, almost all these approximation schemes have been randomized or were randomized at some point. And so it'd be good to make them deterministic. And the only result so far was this one from, I believe, Stock 2022 by Rosen et al., where they give a near linear time deterministic approximation scheme. But unfortunately, this runtime dependence on capital U pops up in their in their final result. Okay, so finally 15 minutes into the talk, I can say what the new result is. It's a deterministic 1 plus epsilon approximation algorithm for the transshipment problem. It works with positive real edge costs. It works with arbitrary real demands. And the running time is a relatively clean 1 over epsilon squared m polylog n. So it hits all 3 of those desiderata. Okay. That's a problem. Okay. And on top of this, I'd like to think that it's relatively simple compared to these other more recent approximation schemes for the problem. I have to say that with a caveat that these were designed with distributed and parallel algorithms in mind. So that necessarily creates some complexity. But even if you try to look at just the sequential variance of those, I believe my algorithm is a little bit more simple and the analysis is a little more straightforward than those past works. But that's, of course, up to opinion. Okay. So my algorithm uses very directly this boosting framework by Zuzik that I mentioned. And what Zuzik does is he describes how to compute a 1 plus epsilon approximation by using several calls to a weak approximation, but not for the transshipment problem itself, but the weak approximation is actually for the linear programming dual to the transshipment problem. Zuzik describes how all these known approximation schemes end up implicitly using this framework, even if they don't necessarily recognize it as such. And one common theme is that you can take certain groups of these approximation schemes and recognize that they are going towards a particular goal, but you can reinterpret this alternative goal as going for the boosting framework. So there's a little bit in the paper about how, oh, here's one way to apply the boosting framework, and these papers do it. And here's another way, and these papers do it. So thanks to these intermediate steps that are kind of common between things, I don't actually need to get into the linear programming dual of transshipment. Instead, I'm going to describe one of these alternative routes that eventually take you there. And this alternative route is something called a linear cost approximator. So a linear cost approximator is a matrix, capital P, and it's not a coincidence that I use that letter again. P has the vertices indexing its rows and some arbitrary number of columns K. And we call it an alpha approximate linear cost approximator if P needs to be based only on the graph itself and its edge costs. When you're constructing P, you can't use your knowledge about the demand vector yet, because you're actually going to need to apply P to several different demand vectors. And then what needs to happen is when you do P times any demand vector B, and sum up the absolute values of the matrix you get, or sorry, the vector you get, that sum needs to be greater than the optimal cost of routing B, but at most alpha times the optimal cost of routing B. So you should get an alpha cost approximation using just this linear operator on the demands B. This is essentially the same thing as what Sherman was doing in hindsight and applied to transshipment. But in my opinion, a little bit easier to describe and intuit what's going on with it. So just a little bit more about the boosting framework. Zuzik explains that if you do manage to find an alpha approximate linear cost approximator, then there's a straightforward transformation that will let you apply the approximator a couple times to your demand vector B and do a tiny bit more calculation, and you'll end up with an alpha approximate solution to the dual problem. And therefore, you're ready to use the boosting framework. And in particular, if you can apply both P and its transpose to an arbitrary demand vector in some amount of time capital M, then you can get your 1 plus epsilon approximation for transshipment in a total of 1 over epsilon squared, alpha squared, m polylog n time. So for some of these past works, and in particular what I'm talking about today, the entire goal comes down to finding a good linear cost approximator. One where this approximation ratio alpha is relatively small, preferably a polylog, and one where the time it takes to apply both P and P transpose is also as small as you can get it, preferably near linear in the size of the graph. All right. So I am going to spend a little time explaining my motivation for the final algorithm. And so we're going to have to take a brief detour into how some of these past approaches found their linear cost approximators or other solutions. All of the past approximation schemes, with the exception of this deterministic one from stock 2022, they start by taking our graph problem and embedding the shortest path metric into low-dimensional Euclidean space using a random Bourgain embedding. So they embed the vertices into the low-dimensional Euclidean space so that the Euclidean distance between vertices is approximately equal to the shortest path distance between them back in the original graph. Once they've done the embedding, they now have a bit more structure than they used to have when they were working with the arbitrary graph. And so they go about trying to find flows directly between the embedded vertices. And in particular, they compute what you would call oblivious flows between the vertices. And in this context, an oblivious flow is one that for each vertex u, you look at the demand on u. Well, actually, you don't even look at the demand on u yet. You look at the vertex u and the location of all the other vertices, and you figure out what are a bunch of flow paths I would like to have u, and what it has, and I'll just multiply the amount I would send along those flow paths by u's demand, completely ignoring the demands assigned to all the other vertices when we're picking these flow paths for u. And if u once flow, then you'd have like reverse flow paths. So they pick these flow paths based entirely on the location of u and the other vertices in the embedding. And when you later learn what the demands are, that'll tell you like how much to scale the flow in those paths. And the hope is that the paths for like positive and negative demands will coincide in a good way to kind of cancel out, and you won't be contributing to the total cost. I'll make all this more precise in a little while when I actually show you one of these things for transshipment. So a nice thing about oblivious flows is that you pick the flow paths ahead of time, and then you scale them by the demand vector. And so they're usually pretty easy to describe by a linear cost approximator. And that is more or less exactly what happens in these 4 works, including mine from last fall. I'm going to focus now on an approach used to get the oblivious flow in 2 of these past works. And that is by solving something called the geometric transportation problem. So geometric transportation is essentially the transshipment problem again, except you're given points in, we'll say, Euclidean space, and you're wanting to route flow through the complete graph on your points, where the cost of each edge in the complete graph is equal to the distance between the points in the space that you're working with. So down at the bottom, I have a simple example. There's a blue point there with a demand of 3, and it's sending 2 units of flow to a red point with demand -2, and 1 unit of flow over to a red point with demand -2. And so the final cost of this solution to transportation, you would take 2 times the length of that one vector plus 1 times the length of the other vector, and continue with all the different flow paths that you chose. So when you do a Bourgain embedding, you do distort some of the distances, but fortunately, you distort all of the pairwise distances by a relatively small order log n factor. And therefore, if you can solve, say, the optimal transportation problem, or if you can solve the transportation problem exactly, then you can take the flow paths you picked in Euclidean space and kind of project them back to your graph, and it'll end up being an order log n approximate solution to the original transshipment instance. And that'll work for all possible demand vectors B, because all of the pairwise distances have not been distorted by too much. And that makes it pretty good for building a linear cost approximator.
Emily, can I maybe just ask whether you could clarify for the audience who hasn't seen Bourgain's embedding, where you embed into?
Yeah, so you map each vertex into order log squared n dimensional Euclidean space. And then the actual metric, you use the L1 metric in Euclidean space, or you could use the L2 metric. The distances are going to be distorted by only order log n factor. So they will only grow, and they'll grow by at most log n times the original distance. Now, I say all this to kind of motivate why we're looking at transportation, but I'll also admit that it's not too important to know these details for this new result, because I don't end up using Bourgain embeddings. They're mostly used, this part's mostly to build up intuition for what comes later. Okay, so I'm still not going to quite talk about my own transshipment algorithm. Instead, I'm going to talk a little bit more about transportation, because approximation schemes for transportation, or at least approximation algorithms, had a similar trajectory, where there were good randomized approximations, and then finally we got a deterministic one last fall. And so looking at what was done to de-randomize these transportation algorithms, that is directly what I did to motivate this new algorithm for de-randomizing approximation schemes for transshipment. So I'm going to, at a very high level, describe how to get a loose approximation for transportation, how to de-randomize it, and then what we should try doing for the actual transshipment problem. Okay, so let's say you have an instance of the transportation problem. It's a bunch of points in low-dimensional Euclidean space, and for these figures, I'll just stick to points in the plane. So we're going to build this thing called a quad tree around the set of points. The quad tree has a root or level 0 cell, which is a large axis-aligned box that's a little bit bigger than you need to surround all the points. You pick a box to surround them, and then you randomly shift it by some amount chosen uniformly at random between, say, 0 and the diameter of the box. And then you proceed in a series of, or a sequence of iterations. You just built the cells at level I, or level I minus 1. You look at all your level I minus 1 cells, and if any of them contain 2 or more points, then you go ahead and you split the level I minus 1 cells into 2 to the d level I cells, where these new little cells have as a parent the big cell that they came from. So in the plane, you end up splitting squares into 4 smaller squares. That's why it's called a quad tree. In 3D, we call these octrees. And generally, we stick to quad tree. All right, so the actual routing of flow is based on the location of the points within this quad tree that we just built. Imagine that we know what the demands are for right now, so I can describe an oblivious flow. We're going to take each point and we're going to descend its demands worth of flow to the center of its highest level cell. So that would mean we send it to the center of the leaf cell that contains the point. And then it's another iterative process, except we're going from the leaves to the root. Once we've sent demand to the center of the level I plus 1 cells, we look at what the net demand is that reached the center of each of those cells, because some of it may have been positive and some of it may have been negative. We hopefully got some cancellation. And we send that net demand further up the tree. A level I plus 1 cell is going to send its uncancelled demand to the center of its enclosing level I cell. Repeat for all the different levels until you're finally sending flow to level 0. And at that point, everything should be canceled out because there's exactly 1 root cell. The cost of this flow is just the non-zero demand times distance that it travels as you go. And it turns out that the cost is a pretty decent approximation on the original transportation problem, even though we used such a simple routing scheme. So in particular, if an optimal algorithm would want to route some x units of flow between points P and Q, well, there's some, say, plus x units of demand that P had that were satisfied by sending it to the minus P or x units of demand that Q has. These x units of demand will work themselves up the quad tree and eventually run into each other and cancel out. And we would expect that to happen after traveling only a distance of order log capital U times the distance between P and Q. Well, if the optimal solution is sending flow directly from P to Q, the cost of that's going to be at least x times the distance. So this implies we have an order log U approximation. The actual routes that we send the demand are figured out independently for each point. We don't care about the demand assigned to any other point when we're doing so. And so this is an oblivious routing scheme, and we can compute its cost with a linear function of the input demands. Okay, but now say we want to de-randomize this scheme. We can't afford to randomly shift the box anymore. That's a form of randomization. And so what we do instead is we ask a question for each point. If I were to just fix a deterministic quad tree and pick some level I, how much demand would we expect to be sent to each of the cells at level I? So for example, we have this point down here, this point here in the upper right. If I were to shift that whole box somewhere between 0 and diameter units along the diagonal, there would be a relatively small amount of shift where the point would still live in the upper right square, say a quarter of the time. And so we would expect a quarter of the demand to go to the center of that square. There'd be a tiny, tiny amount of time where we'd have the point living in the bottom right square. We would expect a tiny amount of demand to go there. And then we'd expect quite a lot of demand to go into the bottom left square. And then we do a cost computation based on those expected values of how much demand goes into each space. And we get another linear function of the demands that now deterministically gives you an order log U approximation. And if you want to, you can also get an oblivious flow based on this by sending an amount of flow proportional to the expected proportion of demand that you send to each square. Okay, so this is a strategy used in these two works. They perform a single random Bergain embedding into low-dimensional Euclidean space, and then they construct a single deterministic linear function based on what would you expect to happen if we were to do a random shift for the transportation instance. Put these two things together and you get a linear cost approximator for the transshipment problem, and you can apply the boosting framework. But then this leads to two questions for trying to de-randomize transshipment itself, or at least two possible approaches we might take. So one, maybe we can de-randomize the Bergain embedding somehow. If we can deterministically find a way to embed the points in Euclidean space with low distortion, then we could take our approximator for transportation, combine it with a matrix describing the embedding, and we get an approximator for transshipment. That's one route we could take to solve the problem. In fact, that's what the second point is. If there was some way to de-randomize the embedding, we would still need a way to describe the whole embedding. Oh, no, sorry. Yeah, so one way would be find a deterministic way to describe the embedding and then apply those ideas that we just saw for transportation. Another idea would be to do a little bit more directly what we did with transportation. Maybe we can just figure out what we would expect to happen with a random Bergain embedding that is then coupled with a transportation solution and get a matrix to describe the expected costs. But the unfortunate thing is I don't know how to do either of these approaches. Bergain embeddings are somewhat complicated. I know of one result claiming to make them deterministic, but I don't think it's been peer reviewed yet. And I don't even know what the running time is to get the deterministic embedding. So the main idea behind this new transshipment algorithm is we're going to take our inspiration from transportation, but instead of going through a Bergain embedding to get to transportation explicitly, we're going to apply all those ideas more directly to a random embedding into a tree metric. Basically like what was figured out by Fekhorenfall and others back in 2004. So they described a way to take our graph and embed its vertices into a random tree metric so that we have an expected distortion of order log n for any one pair of distances. Very briefly, to remind you how this works before I kind of describe its construction, each node within the tree metric represents a cluster of vertices from the graph, with the designated vertex being its cluster center. And the way we could use this tree metric to get a good oblivious flow and linear cost approximator, or to get an oblivious flow at least, would be from the leaves up, we do kind of similar to what we did with the quad tree. We send unmet demand from cluster center to cluster center up our tree, hoping things cancel out relatively quickly before we reach the root. If you fix a single demand vector B, the expected cost of using the strategy would be order log n times the optimal, because the expected distance between every pair of vertices has been distorted by only log n. So that sounds like we're almost done then, but with this embedding into a tree metric, there is no guarantee that all distances have been preserved. There might be some distances that actually got distorted by omega n. And for a good linear cost approximator, we need all possible demand vectors B to work simultaneously. So we can't just use this kind of scheme directly to say, get a quick, easy randomized algorithm. But we can take inspiration from it to get a deterministic algorithm. So let me describe how the tree embedding works, and then I can say how to kind of essentially de-randomize its cost. So say I have a 2 approximation of G's diameter, call that delta. We're going to pick a permutation of the vertices uniformly at random, and some value delta prime between delta over 2 and delta, also uniformly at random. And then for each I from 1 to n, we're going to build a cluster I with a center vi. And what that cluster does is we're going to claim all the vertices that don't already yet belong to a cluster that lie within distance delta prime of vi. So maybe we grab these 5 vertices for v1. And this box contains a lot of vertices close to v2, but a lot of them have already been claimed for the first cluster, so we only take those lower left 3 for the second cluster. I'll take those 4 for the third cluster, and poor v4, it only gets 1 vertex for its cluster because the only other candidate was already claimed for cluster 2. Okay, and then finally, we can string everything together as a big tree by taking the cluster centers and attaching them to a root with appropriately weighted edges. And then we recursively build trees for each of the clusters. All right, so that's one way to describe a random tree embedding. But in order to...
Maybe just to say, like when you say approximately weighted edges in the tree, right? You mean you're putting delta on it, right?
Yes, but I'm not really going to use it. I'm not going to use that fact so directly, so I didn't bother writing it down.
Okay, that's fine.
I just wanted to say how the clusters are formed.
Yeah, okay, I see. Makes sense.
All right, so that's one way to describe how the clusters are formed. But I'm going to kind of turn it around and say, given a vertex U, which cluster does U belong to? So we randomly pick a delta prime and we randomly pick a permutation of the centers. U is going to go to whichever cluster I is the smallest I, so that the distance from U to VI is at most delta prime. Whoever is from the subset that are close enough, whoever got to the front of the line. Using that view of things, in principle, it's possible to describe a linear cost approximator based on these random tree embeddings. So for a given vertex U and delta, we can exactly compute the probability that U is going to go into any one cluster I. We can say that we'd like to reassign a proportion of U's demand from U to each cluster center based on the probability that you would go with that cluster. And then to kind of model the whole tree, we consider a geometric sequence of different deltas. I'm going to start calling them reaches now, because they're kind of like, how far out do we want to reach to send flow? So we consider like cluster centers within distance 1, and then within distance 2, within distance 4, and so on. And imagine sending part of U's demand between these different cluster centers proportionally to how likely you would be to live in each cluster. This high-level idea would actually result in a order log n log u approximate linear cost approximator. So it sounds like great, we're pretty much done, but there's a big problem here. At every reach, every vertex has a choice of up to omega n different clusters to send to. And so if we compute all of these different probabilities of where to send the demand, we're going to end up with an approximator that contains n squared non-zero values. And it's going to be very slow to actually evaluate the thing.
Emily, can I ask another question? And that is,
yeah, please.
So when you're describing this, right, where's it that where's the permutation going in, right? Like you have a random permutation. Shouldn't you, if you want the real approximator, shouldn't you also go over all possible permutations?
So in a couple slides, you'll see a formula that shows you can compute these probabilities without considering all the permutations.
Okay, but basically you're fixing one, or you're okay.
No, I am considering. I'm computing the probability that you would want to send to a particular center for all possible delta prime and all possible permutations.
Yeah, I see.
And that can be
what I'm thinking. Okay, and this still gives you like you can still represent that succinctly, and I think that is kind of surprising. Okay, that's good to know.
Excellent. Yeah, or at least for a particular choice of cluster center, you can compute that probability exactly with a relatively simple formula. Okay, but unfortunately, we can't afford to do it for all possible cluster centers. So the second big idea behind this algorithm is to rely on this thing called the Thorpe-Zwick distance oracle to greatly reduce the number of cluster centers that we have to consider. All right, so fix any integer k greater than or equal to 1. This distance oracle can be constructed deterministically in kmn to the 1 over k polylog n time. It'll end up having space kn to the 1 plus 1 over k, and you can use it to get a 2k minus 1 approximation of distances in only order k time. In particular, if you set k to be log n, you'll get order log n approximate distances, and the construction time will be m log to the order 1n. And the space usage will be m polylog n as well. I'm not going to use the distance oracle for its intended purpose. Instead, I'm going to rip it open and look at how it's constructed and take advantage of the bits of data that it holds. So the oracle stores a sequence of vertex subsets that I'm going to call samples, where the 0th subset is all the vertices and the kth subset is the empty set. For each vertex u and for each index j, u gets assigned a bundle piece, which is the set of sample vertices in A of j that are closer than all sample vertices in A j plus 1. And then u itself gets a bundle, which is the union of all the bundle pieces. The deterministic algorithm, not only does it construct an oracle that has small total space, but if you really dig into the details, you see that each individual bundle has relatively small space. It only uses k n to the 1 over k log n different vertices. And that's log squared n, I believe, if you set k to be log n. Okay, so now we're ready to actually see how an oblivious flow is going to work. So the intuition here is fix a vertex u and some reach delta. And we're going to try to figure out how to reassign the demand of u. And to do so, imagine we have this parameter lambda that's increasing continuously from 0 to delta. If I really wanted to follow the tree embedding literature, I would start with delta over 2, but we're getting a loose approximation anyway. We may as well make it a bit simpler. We're going to reassign portions of the demand v of u to various vertices in u's bundle. And the idea is, up until moment lambda, we should have reassigned a total of lambda over delta. To know where we're doing the reassignments, fix a lambda, and consider the largest index j so that bundle j has at least one vertex within distance lambda. We're going to be sending the next little bit of demand equally to all members of the jth bundle that are also within distance lambda. So here's the actual algebra involved. I'm going to let P VU delta be the proportion of BU that we reassign to V. For a fixed U and index J, bar Bj U lambda is just those vertices of Bj that are close enough within distance lambda. And lambda J plus would be the smallest distance necessary before you would stop sending to anything in Bj. Once lambda hits this value, we're going to start sending to either Bj plus 1, or we've just hit the maximum possible value for lambda. If we sort bar Bj, its vertices in increasing distance order from U, then this formula tells us exactly what proportion of the demand to send from U to any of these vertices Vi. The term on the left handles the bits of demand you're going to be sending to everything in BJU until you hit lambda equals lambda J plus. And the sum on the right is for initially, let's say you're working with V2, initially you're sending almost all the demand to V1 and V2, and then a little bit less to V1 to V2, V3, a little bit less to V1, V2, V3, V4, etc. So you don't actually need to enumerate all the permutations. This formula will get you there. And you can compute all these values in time near linear in the number of them by doing dynamic programming essentially with the summation. Once we know how we'd like to reassign demand, this leads to an oblivious flow for the transshipment instance. So if I have two adjacent reaches, delta and 2 delta, I'm going to, and I take a vertex U, I want to create a flow path for U going between two vertices V and W. We'll take the proportion assigned to U for reach delta, multiply by the portion assigned for W at reach 2 delta, and that'll be the proportion of the demand that goes along a flow path between delta and 2 delta. And so the total amount of flow we'd send along the path would be that product times B of U. Do this for all the different pairs V and W. If delta naught is the highest reach in the graph, which will be, again, a 2 approximation of the diameter, then we finish things up by just picking an arbitrary vertex R and sending whatever proportion of U's flow reaches any vertex W at the very largest reach times B of U units to R. And everything will cancel out by the time it reaches R. And this will actually solve the transshipment instance. So you can argue that the way we picked vertices to receive a non-zero amount of demand, if we're sending flow between reaches delta and 2 delta, each of those flow paths is going to have length at most 3 delta. And so we can upper bound the cost of sending between V and W by this summation. All the U's that might want to send between them, 3 delta times that product. That's a linear function in the demands. The individual bundles are not too large.
Is there now a 2 missing in the summation? Like, should the third term be PWU2 delta, or is that on purpose?
Oh, yes, you're correct. That should be a 2. Thank you.
Okay, just to be
I may have prepared some of these embarrassing.
No, that's good.
I'm surprised I'm as awake as I am. So then, yeah, that's a linear function of B. Not only that, but because the individual bundles only have size log squared n, the number of flow paths that receive any flow at all is going to be n, or Yeah, n log to the fourth n, and then you have another log u factor for the number of reaches. We can describe this whole thing with a small linear cost approximator. Okay, this one a little slower than I expected. So I guess I'll say what this lemma is and say its consequence without the proof. So the main reason all of this works is essentially the same reason that random tree embeddings work. If I'm wanting to know how much demand I'm sending from U to W versus how much I'm sending from V to W within the same reach, the difference between all of those summed over all the different W's. So basically the proportion of demand that doesn't get canceled out when it reaches vertices that reach delta, it's at most order log squared n times the distance between U and V divided by delta. And what this lemma implies is that if the optimal solution were to try sending flow between U and V, then the cost to send a unit of the uncanceled portion of that unit when it reach delta, it's only going to cost 2 delta over delta times that expression. So, or 3 delta over delta times that expression. So order log squared n times the distance to send to the next reach up. That's a unit of flow the optimal solution wanted to send, so that's a log squared n approximation on it. There's log u different reaches, and so we get a log squared n log u approximation for the whole thing. Okay. In the interest of time, I guess I'll just briefly say the proof of that lemma, very similar to the proof that the random tree embeddings don't distort distances by very much in expectation. And the main thing you need to ask is, across the various choices for lambda, what proportion of the demand is being sent to different vertices? And it's almost exactly the same argument with this one consideration that U and V might be sending to different indexed bundles. So we don't have quite, that puts a little bit more looseness into the analysis, but there's only a small number of choices for lambda where they can be sending to different bundles. Okay, so all that is enough to apply the boosting framework when you have small edge costs. In hindsight, this turns out to actually have been pretty similar to what was done at stock 22, even if I came at it from a very different direction. The main big difference here is that I'm kind of motivated directly by all this tree embedding stuff. And after knowing how I wanted to send demand, I let up a little bit more, I guess. I'm sending flow directly between just arbitrary choices of bundle vertices. This stock 22 result, they still use a bit more structure. They're trying to send between nested cluster centers, which I think makes things a bit more complicated. All right. And I guess with just the minute I have left, I'll say, if you want to get rid of that dependence on capital U, the trick is to consider a sequence of minor graphs where the edges that remain are the only ones useful for a particular reach that you care about. And occasionally, if you think you're about to get a big sequence of minor graphs that are all identical, you kind of compress the stack. And what ends up happening is each edge only lives for about log n different levels. And you lose a log n in the analysis instead of a log u, because for a pair U and V that want to send flow between each other in the optimal solution, there's only about log n different levels where the cost of doing that is meaningful in any sense. And so you multiply by log n instead of log u. And you get your log cubed n approximation. Boost it, and you get the main result. Okay, so sorry I ran right up against the time bound, but I'd be happy to take any questions that you still have. Thank you.
Thanks so much for the talk. thank the speaker. So there's some applause already appearing. Yeah, thank you very much for the talk. I think it's nice that you took your time, and this was actually really a very nice presentation of this very neat result. Let me start with a question until we have one in the chat.
Sure.
Just do you have like a good intuition for why it's okay to really just use the points in Torop-Zwick? Like, is that just something that fell out of the analysis, or is that something that like what do you think is the reason that you can really just look at like one level and then at log and points instead of going over all these points that are in there? I think to me that is kind of magical. Like it's kind of the main thing in here that's really surprising me a lot.
Yeah, in which case I wish I had spent more time on this proof, I guess.
No, I think that's fine. It's just, yeah.
I originally looked into Torop-Zwick because I didn't want to take the time to compute all the shortest paths. Like, I didn't want to spend n squared time computing all pairs shortest paths, even for
that makes sense.
A well-structured graph. And I thought, all right, well, I'm going to need some easy to construct distance oracle, and this is the one that I know of. And then I realized that's still not enough because I can't actually afford to even write down the n squared distances. The reason things are okay, well, if I had a set of candidate clusters that I was going to focus on, and I knew I only cared about those candidate clusters, the analysis would be exactly the same as the random tree embedding.
I see.
And now the big issue here is that U and V are going to have fairly different bundles depending on which sample vertices are close to U and V. But after looking at it a while, I realized what happens is if they're sending two different bundles, then there is a sample level that has been reached by one of them, but not the other. Well, that can only happen for about lambda different choice. That can only happen for about, distance different choices of lambda, where one of them has managed to reach a bundle AJ and the other hasn't. And then if they're aiming for the same bundle or the same bundle index, then that point it starts to look almost the same as the tree embedding analysis, where each additional vertex where they could be messing up is a little bit less of a problem since you're spreading things out with a random permutation.
I think that makes a lot of sense, actually. That makes a lot of sense. Thanks a lot. I think that's good.
Yeah, welcome.
Okay. I don't see any other questions in the chat. But I think that's fine, given that you talked for an hour. I think it's maybe best to just leave it at that, and then we'll basically end the session and the talk. And then there's a launch feature, and in the launch feature, basically you will see like some tables and some seats. It's just like a graphic interface, and you can click on the seats and then take a place, and then we are all like sitting together and can talk a little bit and socialize. So I think this will be happening very briefly after the stops, which I think will initiate very soon.
Yeah. Okay. Yeah, I'm happy to stick around for a little bit. I haven't eaten anything, so I might grab a pastry at least.
That is also fine. That is also fine. Normally we don't stay for that long. That's good.
Okay.
Right. Thank you for the talk.
Yeah. Will it be obvious how to get to the?
I hope so.
The
yes.
social part.
Yeah. No, this will just end, and then we will be heading into the social part.